Hi, everyone, and welcome to the Caribbean Connect, where students all over the Caribbean who have this one thing in common: CSEC, information technology, CSEC, math, can come to get solutions, can come to get answers. Um, Today's session targets programming and problem solving of the information technology syllabus, specifically section 7. Uh, so for those who are interested in locating the syllabus, the CSEC syllabus is totally free. If you go to the CSEC store, you create an account, you add the syllabus to cart, and you can download it. Um, there are other locations, I believe, that I guess some people have downloaded it and re-uploaded it and have it accessible. But if ever you need the latest version of any syllabus, feel free to check out this site. Okay. So the content that we will be covering will be strictly based off of the CSEC syllabus. For now, nothing more, but definitely nothing less. So within section 7, which is problem solving and program design, we could identify some of the general objectives, um, such as developing cognitive skills to solve problems, developing the competence in applying a structured approach to solving problems on the computer. This snippet was taken directly from the syllabus guide. So this is what we will be looking at targeting in today's session. All right, and a little bit more. Now, before we jump into the session, I want to point out that programming carries the most marks in the CSEC SBA. It also carries the most marks in your exam. Hence, this is why I decided to start here. It's also a topic that students tend to get problems with if they don't have a proper foundation. All right, so let's just jump straight into it. So, what are the steps in problem solving? Now, we are not speaking specifically to a programming problem here. This could be any sort of problem in the real world. So, the steps are: you define the problem, you propose and evaluate solutions, you determine the most efficient solution, you develop an algorithm to solve the problem, and then you test and validate the solution. So let's try a scenario here. You have a roof that is leaking, or a customer comes to you, you do maintenance work, and you are given a job to see about a roof that is leaking. And this is for a school. School is going on. So based on this, you get an idea of what the problem is, the setting around the problem. Now, if we were to talk about solutions, or we propose solutions, we could say, let's put a piece of flash band on it. For those who don't know what flash band is, it's something like a piece of tape used to clog areas that may have a leak. And it's sort of a cheap solution. It's a cheap yet very effective solution. Another person can say, let's change the sheet of galvanized where it's leaking. That's another solution. Somebody else can even say, let's just do over the whole roof, because if one portion starts to leak now, and this roof was built around the same time, then a month, 2 months, sometime in the near future, another sheet of galvanized might leak. Somebody else might have a grand idea to just put a bucket to absorb the water because it's school time right now. And if we have to do any long-term repairs to this roof, it would affect classes. So it may not be feasible at this point in time. So this should give us a general idea that we're looking at all of the possible solutions in order to determine the most efficient solution, which is the third step, determining the most efficient solution. And of course, once you've determined the most efficient solution, or the most feasible solution, as I may say, you develop it. So it says here develop the algorithm. Algorithm sounds sort of like a kind of weird word. All right, so we'll dig into that algorithm to see exactly what it is. Then we test and validate the solution. So is it that we fix the roof with one of these solutions and then we just go about our business? No, we don't wait until rainy season comes or rain starts to fall and we realize we fixed the roof, but the roof is still leaking. We need to test to make sure that our solution actually solves the problem. All right. And this is what problem solving, not just programming, but problem solving in general is about. But when we apply this to program solving and information technology, this is exactly what we're looking at. So another objective within the syllabus guide said that we have to be able to use the divide and conquer approach to decompose larger everyday problems into smaller tasks. So I used two trivial examples here that I think most of my Caribbean students could relate with, making macaroni pie. So I think we know about macaroni pie and callaloo on a Sunday. Based on what island you're from, if that's not the thing on the Sunday, I would really love to know what is. All right. Um, and building a house. I think we all have an idea some of the steps you take to build a house. And building a house isn't such a small endeavor. So if we're building a house, we could break this up into seeing about the land acquisition. We could see about this in terms of the foundation. We could look at the roofing. We could look at the electrical. We could look at several different smaller problems or smaller tasks that when all are executed, we get a built house. Similarly, making macaroni pie. So we could look at greasing the dish. We could look at making the mixture for the pie. But we would put cheese and maybe onion and maybe egg and so on in a blender to blend up. We could look at boiling the macaroni before we put it in the dish. We could look at baking the pie in the dish in the oven. So we have different subtasks that we can, if all put together, help us accomplish our problem or find a solution to our problem. All right. And it's imperative that we do things this way because programming is a sort of subject that you need to think logically in order to develop solutions to problems. So earlier we spoke of the algorithm, right? And in programming, we have several tools that we use to solve problems. One is algorithms. One is narrative algorithms, to be exact. So a narrative algorithm is a finite number of concise steps written in a logical sequence used as a solution to a problem. So your simple solution here, or your solution should be so simple that a 6-year-old or a 7-year-old should be able to read and follow these instructions and execute it with ease. Hence, we say it must be concise. So here I have an example of a narrative algorithm. Now it's steps. So I have step 1, 2, 3, 4, 5, and 6. And my first step actually says start, and my last step actually says stop. Now, different persons try to represent narrative algorithms slightly differently. But because we defined an algorithm as a finite number of steps, we are going to have a definite starting point and we are going to have a definite ending point. So we specify this in our algorithm. When we transition from our algorithm, even into a program such as like a Pascal program, which most students, at least in Trinidad, for example, still apply when they're doing their SBAs, you're going to see words like begin and end. So when we convert our narrative algorithm into Pascal code, we replace the start with begin, we replace the stop with end. So your narrative algorithm should be able to be converted into different versions of solutions. Later on, you all are going to hear about flowcharts. You're going to hear about pseudocode. You're going to hear about Pascal code. You're going to hear about IPO charts and so on and so forth, right? But just not to make you too overzealous or probably to make you too worried. Let's just continue with this narrative algorithm. So after we start, so this narrative algorithm, sorry, is to find the perimeter of a square. So we ask the user to enter the length of one side of the square. Then we accept the length. Why are we accepting the length? So this algorithm is more related to IT. So this could be implemented as a computer program. So if a user is to type in the length of a square, then we have to accept that value. We have to store that value somewhere, right? So we accept the length. Now that we have the length, we can calculate the perimeter in step 4 here, and we have it as length plus length plus length plus length, because a square has 4 sides that are all equal. So we add the length 4 times. Now someone could argue, we could have just said length multiplied by 4. And you will be absolutely right. And that brings me to another point with regards to programming. Most instances, you will realize that there isn't only one solution to a problem. And this is the beauty of programming. 2 students, 2 groups, 5 groups doing SPAs can have 5 totally different solutions coming up with the same answer. And we see here why something like that is possible. Now that you've calculated in step 4 the perimeter, you will want to display the perimeter so the user who entered the length would know what the perimeter is. At that point, mission accomplished, and we stop. So here I have now an IPO diagram. IPO, by the way, stands for input, processing, and output. We have one thing extra in this diagram, which is a storage area. So in some instances, we actually use storage as well. So if we are to define these components here, input is anything that would be going into the computer. So later on, you would see me do videos giving more details of inputs and processing and so on. But input is basically anything or any sort of information that goes into the computer. So in the last algorithm, we asked the user to enter the length. So they would have punched in a value on a keyboard and that would have been stored on the computer or input onto the computer. Then we have the processing. The processing would have been doing some sort of calculation, whether it's an arithmetic calculation, whether it's some logic-based calculation with the data that you input. So where we added the length 4 times, that would be classified as processing. And in this diagram, I don't think, for at least for this algorithm, we would not have used storage. We would have just done the calculation and we display the answer. And output, we could see that the word output and the word display are synonymous. If ever we're having issues in identifying terms, output, display, print, write, all of those words that are synonymous with output, we can use interchangeably. But the concept of an IPO diagram, we have to use the words input, processing, output, and storage. With that said, we are now looking at another representation of the same solution that we did. This is your IPO chart. So an IPO chart is another representation of a solution, as we said before. It's in a tabular format where the input, processing, and output are in separate columns. So we have those as the titles. So for this question, our input was the length. We read the length or we accepted the length. But because we're looking at words more synonymous with input, we just say read. So I may read that would be input. And if I do the opposite, I write, that would be output. So I read the length, or the computer would read the length, or the program would read the length. Then in terms of processing, we accept the length. So that still kind of classifies as processing. As much as the user would have inputted or punched it on the keyboard, we still have to store that result somewhere. Later on, when we learn about variables and all of these awesome concepts, you will see what we mean. But for now, accepting the length would be a process. Now that we have the length, we calculate the perimeter, and here I have the formula for calculating the perimeter. Some people, when they do IPO charts, they just say calculate perimeter. Now, as much as that is fine, we're trying to maximize on marks. And an IPO chart is one of the things that is asked of students to do for their SPAs. So, where we could not be ambiguous and where we could be more meticulous and pay more attention to detail, we give exactly what is needed. So perimeter equal length plus length plus length plus length. If you wanted, you could have said perimeter is equal to length multiplied by 4. Then, in our output window, we have the length, enter length of a side. So we asked the user initially to enter the length of a side. So that could have classified as output because that was something that should have been displayed on the screen for the user to enter. And then when we worked out the perimeter, we actually displayed the perimeter to the user. So we've looked at your brief introduction to programming in terms of Objective 1 and Objective 2 within Section 7 of the syllabus guide. Now, if you want more content like this, I implore you, subscribe, share, and like. Thanks for watching. I hope this adds some value to you.